So part 2, computer communication. Computer communication and the computer bus. That's what we're going to talk about here. These are the objectives of this chapter. So early forms of communication, all out of earshot communications require some form of code. Morse code uses 2 states, dots and dashes for letters. So we have a dot, dot, dash, 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 dot. Those are just long beep versus short beep, long beep, short beep. That kind of thing. That's how Morse code is communicated. So the binary language of computers, we have a bit, which is one single digit, or a switch in a computer, on or off, electrically switched on or off, and that's performed with a transistor. And then we have a byte, which is 8 bits. 8 bits creates a byte. And then we have a nibble, which is half of a byte. 4 bits is a nibble. And then we have a word, we have a kilobyte, we have a megabyte, and then a gigabyte, and these are just multiple bytes put together. So we have words and double words in today's computers, the more modern ones. Again, this class is kind of old. They made some updates, but it's not quite up to date. So a 0 is off and a 1 is on. This is performed with a transistor, so the gate is either switched in one place or the other, on or off, that's it. And then this just scales up to billions and billions of switches inside of a microprocessor. So like in the virtual processors, they make up with programmable field gate arrays, FPGAs, field programmable gated arrays, or gate arrays. They're just matrices of on and off, and they build virtual processors inside of them. And they build Motorola MIPS, millions of instructions per second. In this class, we're probably going to discuss both of those, but they have 2 basic types. They have a RISC, reduced instruction set, and then we have the where every instruction takes the same amount of time, and then we have the complex instruction set, the CISC, where everything can take different lengths of CPU ticks. So one instruction might take 6 CPU ticks, another one might take 30 CPU ticks. And the MIPS, millions of instructions per second, every second it can perform 1 million operations. Everything's broken down into discrete steps. They all take the same amount of time. So here's an example of binary notation. So what we have is we have 8 bits that can either be 0 or 1. And the way that the numbers are represented on the bottom is the value that the upper ones represent, right? So this is an example, but let's just describe what they're doing. So the very first one to the right there, where it says 8 bits at the very top, that is going to be, you can think of it as 2 to the 0 power, and where the 0 is, it's 2 to the first power, and then 2 to the second power, 2 to the third power, so on and so forth. So what you end up with is the possible values in that bottom column, the pound values of the first, the purple box. So it can be 1, 2, 4, 8, 16, 32, 64, 128. If you add those up, that's the biggest possible number that 8 bits can represent. And they just keep scaling up from there. So it's 2 to the 0 power, 2 to the 1 power, 2 to the 2 power, 2 to the 4 power, 2 to the 8 power, and so on and so forth. So that's how the numbers work. So if you wanted to add up a 3, you're going to need at least 2 bits to do that. So you would have a 1 and a 1, and that's where the number values are on the right side. You're going to have the 2 and the 1. 2 plus 1 is 3. So if you add those, that's how you keep adding in a computer. So if you don't want that value, so if you wanted a 5, it would be 101. The 8 bits there, 101, and at the bottom you would add up 4 plus 1 is 5. Because the middle one is 0, so you don't count that 2 in the middle there. Okay, so that's kind of how they work. And let's see, the 1, 2, 4, 8, 16, 32, 64, they're both the same, but it's just an example. So you take the 1 values at the top, where the 8 bits are 1 in the purple box. So we have a 4 plus a 1, they're both 1, right? So we add the 4 plus the 1 on the right, that's 5. So that 0, 0, 0, 0, 0, 1, 0, 1 is a 5. And then for the bottom number, we have 8 plus 1, which is a 9. So 8 plus 1, which is a 9. So that's what those numbers, the binary numbers, represent.